In this segment, I'm going to derive the kinematic equations, which are a set of formulae that describe motion of an object at constant acceleration and follow simply from the definitions of acceleration, velocity, and displacement. So let's write down the definition of acceleration as acceleration is the rate of change of velocity with time. For example, in a velocity time graph, A is the slope of the velocity time graph. Okay, so let's look at this equation we wrote here. So A is dv by dt, so it therefore follows that if we'd like to know the velocity of an object at a certain time t, we could get it by rearranging this equation and integrating. So v would be equal to the integral of A dt, which is at plus constant. Now what is the meaning of that constant of integration? The meaning of the constant of integration is the initial velocity. So imagine that our object reaches some velocity after a time t, that is its initial velocity v0 plus the change in velocity owing to the acceleration. So that's our first kinematic equation, and we'll number it number 1. Now we'll move on to the definition of velocity. Velocity is the rate of change of position with time. V equals dx by dt. Similar to what we did before, we can obtain the distance traveled by an object moving at this velocity by integrating under this curve here. So x equals the integral of v dt. Now we already have an expression for v as a function of time, which we obtained in equation 1. So let's substitute that in. So x now is the integral of v0 plus at, all with respect to time, which gives us v0t plus at squared over 2 plus a constant of integration. And thus before we can ask, what is the constant of integration? Well, it must be the initial position. Where did the object start? And then how far did it travel during the motion? So our final equation here is x equals x0, which is why our constant of integration can be identified as, plus v0t, the original velocity times the amount of time elapsed, plus half at squared. And this we're going to call equation number 2. Now we're going to move on, and we're going to look at another way of defining velocity. Now we're all familiar with the idea of average velocity. So the average velocity is commonly held to be written as v with a bar above it, and it is the change of position over the amount of time that has elapsed. If we're moving at constant velocity, this is the same as the instantaneous velocity at all times. If the velocity is changing, however, this is only the average velocity and might not be equal to the actual velocity at any particular time. So that's the average velocity. So the average velocity is the change in position divided by the change in time. Change in position could be thought of as where do I end up minus where did I start divided by the time elapsed. So that's the first definition of average velocity. However, we can also write average velocity in a completely different way as being simply the sum of the initial velocity plus the final velocity divided by 2. After all, the average of two quantities is always calculated this way. So let's name these two equations. This one we'll call 3, and this one we'll call 4. So we've now got a set of equations which describe motion at constant acceleration in terms of various different variables. But one thing you'll notice all of these have in common is that all of these equations have time in them. Now, it would be really useful to obtain an equation that does not require knowing the time. So let's see if we can derive one from above. So we're trying to derive an equation without needing time. So let's see what we can do. Let's begin with equation 1, which includes time, and we'll look at equations 3 and 4 and see if we can rewrite both of these in terms of time in order to remove it. So let's take the two definitions that we have of average velocity. Since these two are both the same thing, we can put them together. It now follows that 3 must equal 4. Equation 3 must equal equation 4, since they're both describing the same thing. So x minus x0 over t must be equal to v0 plus v over 2. We can rearrange this to make time the subject of the formula, and then we could combine it with equation 1. So let's try and do that now. So time is going to be equal to x minus x0 times 2 divided by v0 plus v. Now let's combine that with equation 1. Equation 1 can be rearranged, so let's just write down equation 1 again. V equals v0 plus at. So from this we can deduce that t must equal v minus v0 over a. So we've got two equations for t. So if we make these two things equal to one another, we can then eliminate t and find a new expression which links all the kinematic variables, position at the start, position at the end, velocity at the start, velocity at the end, and acceleration, without needing to know time. So let's do that now. We'll combine to eliminate t. So let's do that now. V minus v0 over a equals 2 x minus x0 over v0 plus v, which we can rearrange a little bit to deal with some of these factors. So over here, let's collect all the velocity terms together. V minus v0 times v0 plus v equals 2a x minus x0. Now, we'll take the terms on the left and simplify them, and we'll see what happens. So let's use the usual method, first outer, inner, last, for multiplying out two terms in brackets. So the first terms multiplied together gives us v0. The outer terms give us plus v squared. The inner give us minus v0 squared. And the last terms multiplied together gives us minus v0v, still equal to a x minus x0. Now we see from this that some of these terms cancel because v0 is the same as v0v. So we end up with v squared minus v0 squared equals 2a x minus x0, or if we prefer, v squared equal v0 squared plus 2a x minus x0. And that's the last kinematic equation, and so we will name it number 5. So we now have a set of 5 kinematic equations, one that describes velocity in terms of time and acceleration, one which determines displacement in terms of initial velocity and acceleration and time. We have two definitions of average velocity, and finally we have this expression that gives the final velocity in terms of the initial velocity, the displacement, and the acceleration without having to know the elapsed time. And I think there we'll stop.